Right, let's get going. Just a quick reminder of things that are still up in the air as far as you're concerned. There's a homework, there is a final exam, and there are projects. The usual advice that I have is don't let all of them pile up at the same time. But I'm sure you know that. Are there any questions about the homework? Yes.
So for the SPM implementation, right, it's an unbalanced data set, so like when we run it as normal,
right,
it ends up labeling everything negative.
Really?
Yeah.
For all hyperparameter choices?
No, so that's kind of my question is like, I've been playing with like C and the learning rate and everything like that. I guess my question is like with the proper hyperparameters, what sort of like F value should
actually, I have not yet played with the data yet, but with this particular unit of the data. So I can't remember, I don't remember what accuracies I got, but I did hear that the F values were rather low. Yeah.
Yeah, so in my experience, this is a side effect of regularization. If you take the regularizer out, your F value goes up to, say, 0.3, 0.4. With regularization in, it's extraordinarily low, like 0.001.
0.001?
0.001.
So here is something that you can think about. Don't just look at the F value, look at the precision and the recall. One easy way of getting okay, not easy. So here's a sanity check experiment that you should do, which is forget any classifier, just predict all the examples as positive, or all examples as negative, and you can hand calculate the F values, the precision and the recall. One of them gives you 100% precision, the other one gives you 100% recall, and any self-respecting classifier should do at least as is that. I think it's possible that might be, your one of these situations might not even be crossing that threshold. If I remember right, I think someone told me that they got 100% recall if they use a certain value of C, and that gives an F value of 0.3 something.
So without doing the precision and recall, regular accuracy, I was getting 79%.
Right, so I got something like that for accuracy as well, some 70s or something, or low 80s.
Yeah.
But then accuracy does not necessarily mean much if your data is unbalanced. So if it makes you feel better, report the accuracy as well. For the game that we are playing here, let's say that in this round, it's not the accuracy that matters, but you care about precision and recall on the positive label. That's why we measure F values. And if the F values are low, what can we do? I mean, something that one of my TAs was mentioning yesterday. If you think about it, as the semester has gone along, we started off with a data set where you got 100% accuracy, and things are getting progressively worse in terms of the performance. And the point is, real data might have that property. You can't tell before you know that the best performance that you get is only slightly better than chance if you're lucky. And that is what it is. And maybe it's possible, one of the following things could be happening, assuming there are no bugs. One of the following things. Option one, maybe it is your features are not good enough. Maybe the data set is not linearly separate. Another possibility is that your task is unlearnable. Maybe the label is basically not a function of whatever features you have. It's just I'm being cruel. So, but you never know what's going on, right? You never know when you have real data in a real problem in the wild. You don't know which of these is happening. So you report what you get. One sanity check that you could use is try out your other algorithms that you implemented. Try out your perceptron. using a similar, try out average perceptron. If you strongly stand by that, by your code, you should not be getting very different F values for a well regularized, or not regularized, well tuned average perceptron. You know, where all the learning rate and everything is properly chosen. So that could be another test that you could try. But in the worst case, there's nothing we can do. If this is what the data is, that's what we live with. So I did hear quite a few reports about low F values, something not as low as 0.01, but something like 0.3, 0.4, something in that range. So if that's what it is, that's what it is. If you really want to kind of dig deeper into that, I would suggest looking at the precision and recall values. Keep in mind what, so have I ever spoken about precision and recall in the class? So precision and recall are useful when you have unbalanced data. Let's say you have a particular label you care about. And a precision is asking, when my classifier predicts that label, what fraction of times is it actually getting it right? So among the predictions, how many correct outcomes are there? Recall is, the way to remember recall is you recollect the ground truth. So recall is among all the examples of the label that have that label, how many did my classifier discover? What you would like is both of these to be high. In an ideal world, you want both of these to be 100%. And what you have to invariably end up dealing with is what is called the precision recall trade-off. Sometimes you might change some setting in your classifier, and you might get high precision and low recall, or low precision and high recall, and that's what you live with. And a phrase that you might hear sometimes is called equal error rate, where you tune your classifier to get equal precision and recall. I'm not sure why that's a special thing. It's a name. F measure is basically a way of converting the precision and recall into just a single number so that you can do things like cross validation and report rates. Any other questions? Does this, I'm sure this is not a happy answer, but does this give you something to think about? Yeah.
So you're asking for us to cross validate any of which F values in this?
Yes. Yes. I want you to cross validate for F value. Because you want to choose the hyperparameters that try to find the best performance measure according to whatever performance measure you care about. Maybe it's possible that you may cross-validate for accuracy and get a set of hyperparameters that give lousy precision and recall. Why? Because the best accuracy might be the case where you predict all examples as the same label, whereas precision recall don't do that. So yeah, an extreme example that I once encountered was a data set where I think about 99.94% of the examples were negative, and the remaining was positive. And I was asked to train a classifier. Oh boy, that was painful. There we had to do all kinds of dirty tricks, like subsampling the majority class and oversampling the minority class so that we kind of at least give some signal. Nothing really worked. This was the task was deciding when a second language speaker of English makes a grammatical error. It turns out most of the words are correct. It's such a tiny fraction of them that are wrong. But those are the ones that seem to jump out. Anyway, so yeah, this definitely does happen, and it's. I use the homework as an excuse for kind of pushing out more material than I can cover in the lectures. So this is one of those instances. Other questions? Yeah.
For my logistic regression, if I use sigma squared equal to 0.1 for cross validation, I was getting English. When I take it down to it works fine.
When you get what?
When I use sigma squared equal to 0.1,
yeah,
I was getting overflow.
Oh, you get overflow. Oh, yes. So you will get overflow. If you're not careful with implementing logistic regression, you can get overflow. Have others seen overflows with logistic regression? Yes. And there is a very neat trick to deal with that. Let me just very briefly talk about this. This is not really machine learning. It's I don't know what to call it, dirty programming tricks, but Consider the logistic function. So it is log 1 plus e power, or the loss for the logistic function. The log loss looks like something like this, right? You know what? Let's forget this. Let's just say we need to compute some number. Now, if you naively compute this value, if you just meaning you just write this in code and ask the program to calculate the value, it's possible that maybe when z is say minus 1000, the whole thing breaks down because e power 1000 is an overflow. But let's kind of look at this. This is really exactly now when z is minus 1000, the whole thing you're taking the log of e power something. So it should not have an overflow or an underflow. So the way to deal with this is, let's say that this is equal to log e power. Oh, let me just remove the minus because I know I will forget it very soon. E power c. This is the same, right? I've just multiplied. I've taken out e power c. Now, because this is the log of a product, so this is exactly the same as z plus log 1 plus, right? Now, when z is, say, in this case 1000, this quantity is extremely small. It is so small that we can assume that it is 0. So that you're left with log 1, and so this is equal to z plus log 1, so it is z. So what you could do is you look at the thing inside the power. If that thing is really large, that the log loss becomes exactly the power. Thing is the power. This trick is called the log. You can, if you want to get some, find this on Google. You can look for log x. I don't know what the different people call it different things. Let's call it a trick. It's very commonly used when you implement probabilistic models because you have to deal with exponentials and log of exponentials a lot. So what you always do is you keep track of a certain value of, keep track of what the power is, the exponent is, and if it's below or above a certain threshold, you kind of refactor things so that you don't have to calculate. Let me give you another example of this. Consider, sorry, let me just go to another page, the sigmoid function. Sigmoid of z is when z, so I'm not going to derive the whole thing, but I'm just going to, you can derive it. The sigmoid function looks something like this, right? Turns out when z is greater than or equal to some number, let's say 6, sigmoid of z is so close to 1 that you don't even have to calculate it. If z is less than minus 6, sigmoid of z is so close to 0 that you don't even have to calculate it. So you never have to compute exponents of large numbers. So you have to keep thinking about this whenever you have, any time in your code when you're taking log of some exponent, you have to think about these kind of hacks, and they don't really matter because it's really so close to the limiting value that it makes no difference in your performance. But logistic regression, log linear models, exponential models, and such things will need this kind of hacks. Yeah. Other questions, homework related? So one sanity check also is, I would be surprised if logistic regression with proper tuning and perceptron with proper tuning, not perceptron, SVM with proper tuning would be very, very different in performance. So that could be another way of just sanity check for if something is wrong in your code. Another question that came up with the homework was there were some concerns about if you think about all the hyperparameters there are, if you consider the cross product of all of them, it seems like you have to do cross validation for basically forever. For this homework, I'm willing to kind of allow you to justify why certain hyperparameters should not even be considered for cross-validation. If you have a good reason for saying that, say, C equals 0.000001 is not a good one, and based on some preliminary experiment, you can take it out of cross-validation and write it in your report and say, I did not do this because of these early preliminary trials that showed this is a hopeless thing to try. So the reason I'm allowing this, because you will end up doing that when you use machine learning for real. You will end up picking certain hyperparameters and treating them as constants simply because there isn't enough compute for you to meet the deadline, let's say. Any other concerns or questions about the homework? If not, we're going to get back to neural networks. We're going to look at prediction with neural networks. Just to remind you of where we are, we're talking about neural networks. The last lecture, pretty much the entirety of the last lecture was introducing what neural networks are. And as I said, you should think of these as basically directed acyclic graphs where the nodes correspond to, the nodes are called neurons, and edges carry weights, or edges are associated with weights. Information flows along each edge, it gets multiplied with the weight. So the node accepts some input as a vector. What it does is it takes dot product with all the weights and then applies a nonlinear transformation called the activation. So what we're going to do next today is we're going to talk about how to predict with a neural network. I'm going to introduce this entirely using an example, and because I'll introduce this with an example and hope that it generalizes in your head. So that as the running example that I'll use both for prediction and training, let's say that we have this neural network. This is a two-layer network. Keep in mind, in order to define a neural network, what we need is its architecture and the weights. The architecture is the graph that we have, namely the nodes and the edges, and also the activation functions on each node. The weights are associated with each edge. So let's build up, in order to make the prediction, we need all three things. So let's say this is the graph that we are going to look at today. Just so that we have some convention, the inputs, I'll call them x's, the outputs are y's, and there's one hidden layer, let's call them z's. So this is a two-layer network. It's two layers because you count the output layer and the hidden layer. I'm assuming that we always have a bias feature for every node in the network. There is it has one input that corresponds to the bias feature. Just for consistency, I'm giving it a letter, but Z0 is always 1 and X0 is always 1. But just to make the notation kind of consistent, I'm giving it a letter name. But just to remind you that it's a bias, I've shaded this thing, that node gray. In order to define the activation, in order to define the network, it's not. So let's say that we only have, in this tiny example, we only have two inner nodes. Let's say both of these, are correspond to a sigmoid activation function. The sigmoid activation is the exact same thing that you use in your logistic regression model. So what we have really is, this is one logistic regression and this is another logistic regression. But that's not enough. I need to say what the activation for the output node is. Let's say the output activation for the example that we'll consider is the linear activation. What that means is the linear activation is kind of a strange name. It's really an identity function. What it does, all neurons, the way they operate is, given some input x, not the same x that we have here, given any input, what the neuron does is it converts it into activated version of some W transpose X plus B, where A is some transformation. So any neuron takes an input and takes a dot product of the inputs that it gets, adds a bias, and transforms it through some function called A. A is activation. The very special kind of activation is called linear activation, which says A is the identity function, namely it does nothing. It takes the dot product and sends it up. What that means is the output that we get here, because the output is that node Y has a linear activation, the output that we get can be any real number. Right? Does that so far are we all on the same page? Now, what this means is this network takes some input, x1 and x2, and converts it into any real number. Well, not any real number, it converts it into some real number as defined by the weight. So this means that this network is an example for of a network that does regression, right? Because it takes some input and produces some output that's a real number. Linear activations are used for if you need to do a regression. If you have classification, you usually put sigmoid or tan H on top. Usually sigmoid. Now, it's not enough to just specify the nodes and the edges and the activations. To specify the full network, we also need to say what the weights are. Now, I'm going to introduce some naming convention just so that things become easy, but when I introduce it, it's not going to look easy. It's just going to look hideous. The notation that I'm going to use is all the weights. Every edge corresponds to weight, right? Every edge corresponds to weight. All the weights are going to be written like this. It is W from 2 at the bottom and target layer at the top. So just concretely, that node that I've highlighted there is W01 O. And now realize that O and 0 look the same. O for out. This is a weight on the edge from node 0 to node 1. Node 1 in the output layer. It turns out there's only one node in the output layer, so it's just the one thing. So this, for example, this edge will be associated with the weight W02 in the hidden layer. This is just convention that I'm using so that we all agree on something. Yes?
This sort of thing doesn't allow for nodes from like different layers to the same target layer.
Yes, that's right. That's right. This naming convention is crippled just enough that it lets me run with the example, but it doesn't allow for a connection of, say, this kind. Yes. Yeah, this naming convention is only for the example. In fact, you wouldn't even use this in real life because most of the time we would not be dealing with individual weights like this. These are all numbers. Every weight is a number. Most of the time we'll be dealing with all the weights in the layer as one set. We'll think of all the weights in this block as a single matrix. And we'll be calling all of these a single vector. So we'll be just using vector and matrix notation once, well, not in this class, but most of the time it'll be vector and matrix notation. I'm deliberately blowing up the notation so that there is nothing opaque. Other questions? So what we have here is a full network. We have the nodes, the edges. We have the activations, and I've not written it here, but this is a linear, and this is sigmoid. The z's are just ones. So sorry, the z0 and x0 are just ones, and all the edges have weights. Let's pretend that we have finished learning, however we did learning. And today, we have to now make a prediction. We have to make a prediction on a particular example x. But by x, I mean it's really x0, x1, and x2. Let's say we have this particular example and we need to make a prediction. It turns out predicting with a neural network there is really not much of a mystery. What you do is you go one node at a time. So in order to compute the value of z1, You have all the information needed to compute the value of Z1. What's the value of Z1? Z1 is sigmoid of its corresponding weights. So it is W01 H x0 plus W02 H x. Oh, this is confusing. It's W11 H x1 plus W21 H. It's the sigmoid of the dot product. We have all the things we need. We know the value of x0, x1, and x2 because that's the input given to us. We know the w's because those are the weights that we learned, so we can actually compute the value of Z1. Right? It's just, there's no magic there. Similarly, we can compute the value of Z2. So we have Z1 and Z2. We also had Z0 because that was just equal to 1. So now we have all the information. We have Z0, Z1, Z2. We have all the information we need to compute the value of Y. Right? So we just compute the value of Y, and that's the output of the network. So given an input, any neural network, keep in mind, neural networks are defined to be directed acyclic graphs. So there is you can order these nodes in a certain way without ever having repetition. So because it's acyclic, you can go from the bottom to the top, and once you get to the top, you have the output. Any questions? Can you implement this? If you had to, with some amount of pain. Now, one thing to keep in mind is there is any implementation of such a network would necessarily, you have to be a little bit clever with not doing double computation. Like, in order to compute Y, that's not the marker I want. In order to compute Y, you need to compute Z1 and Z2, and then you can go down. But maybe Z1 and maybe this was like a 3-layer network, and maybe there was another layer below this, let's say something like this. And maybe in order to compute Z1, you need to compute X1 and X2 and so on. But if you are not clever about it, if you do your computations in the wrong order, you might end up computing X1 or X2 multiple times. So really, the way to proceed is you go from the bottom to the top, so that you never compute anything twice. So once you compute Z1, you store the value and you never compute it again. And that way you essentially save on computation. Today, most of this process, the forward pass and actually also the training is done using very efficient linear algebra libraries, because what we have there is a dot product. Z1 and Z2 are applying, both of these things before the sigmoid is applied can be efficiently written as the product of a matrix and a certain vector. In this case, the vector is x0, x1, x2. So you can compute these things very efficiently if you can do matrix vector computation, multiplications efficiently, and the devices that we have today that can most efficiently do matrix vector multiplications are GPUs. And that's why basically NVIDIA is making a killing, because they make the best GPUs. So this is the reason why NVIDIA stock is flying high, because deep learning is pushing its apparently video games also, but of course that's not interesting. But yeah, if you have to implement this kind of stuff for real, you would not be doing this like what you do in your homeworks with your own library. Some of you are actually implementing your own dot products and all that. You would not be doing that. Instead, you'd be using some libraries that do efficient matrix vector math. Questions? Now notice that I have only given this as an example. I'm deliberately choosing not to show the general version, but I want you to think about how this generalizes to any network of whatever shape, whatever architecture, because turns out you can actually write that very compactly if you use the terminology of computation graphs. I'm choosing not to introduce that right now. But if you want to read more about it, look up computation graph. All right, if there are no questions, I'm going to move on to the next part of things, namely, how do you learn these networks? How do you learn the weights? The problem of learning is where you are given some data set. And remember, when we say we're learning neural networks, we don't talk about learning the architecture, we don't talk about learning the activations or the layout of the graph. Instead, we only talk about learning the weights. So, in order for learning to proceed, we assume that we have the weights, we assume that we have the architecture of the network. We've decided on that somehow. And we've also decided on, we also have a training set. So, once we have that, you might start thinking about learning. So one of the reasons why neural networks have really become popular now is because there is efficient learning algorithm for this that depends on backpropagation. How many people have heard of backpropagation? How many people know backpropagation? Okay, then I have to teach it. Okay, so the setting for learning is the same as the one that we have in most cases. We are given a training set. The training set is, this is supervised learning. So we have some labeled examples. So we have xi's and yi's. Xi's are input vectors. Yi's could be labels. The labels could be 0 or 1, or -1 or 1, in which case you have binary classification. Or the labels could be real numbers, in which case you have regression. The labels could also, it turns out, be multiple classes. The same ideas that I talk about today can be generalized to multi-class classification rather easily, but we won't get there. For now, let's assume that the label is either a real number or a single bit. We are given the neural network architecture. So we have the neurons, basically the graph, and all the activations. Our goal is to learn the weights on the edges. Now, the first thing I want you to keep in mind is you know how prediction works. Given the weights, your neural network is basically a function that can take any input and convert it to the output. We just saw that. That's the forward pass. The forward pass is the process of taking an input and converting it to an output. Given a weight, you can convert any input to a label. Let's say that we have that, let's just abstract it out into this function called NN. NN is a function, neural network, is a function that can take an input and convert it into a label, provided all the weights were known. So it's just a function. Now, the key idea that we'll keep exploiting is the following. If you have any function that can produce a label, like this one here, we can write down a loss. We can write down the loss for the penalty on that function for misproducing a label or for mispredicting. So for any input xi, if you had a certain set of weights, then you can produce a label. Let's call that y, but let's just call that y. And now I can write down a loss of y and yi. For that particular take up more space, but you can always think about extending this with a regular. Now, once you have written down a loss function like this, you can add up the loss over an entire training set. At this point, it's still a function. Keep in mind, this is just at this point, this is all a function of the weights. So I can write down loss as a function of the weights. By the way, I'm using W again here to represent all the weights in the network and in all the layers everywhere. So the loss of the W that we care about is the sum over all the training examples, sum L, I, and W, and the prediction yi, sorry, and the ground truth yi. So every set of parameters can be penalized by this total loss, or you can think of this as the average loss if you want to divide by the number of examples. A reasonable strategy for learning is to find the set of weights that minimizes this loss. This is what you've been doing for SVM, logistic regression. I mentioned in the last lecture, perceptron, AdaBoost, all of these things. So why not try this for neural networks? So a reasonable strategy is to minimize the loss. Now, we've seen this works for other things. We've seen this work for logistic regression, where you minimize the log loss for a linear classifier. It works for SVM, where you minimize the hinge loss for a linear classifier. It works for perceptron, where you minimize the perceptron loss. It even works for regression. If you're doing regression, you should be minimizing the square loss, not one of these things. All of these were linear models, but the same thing could apply for non-linear models as well, for neural networks. So we can try that. Before we get into the details, any questions about this high-level strategy? No questions, let's get into details. In our specific example that we had, we just saw that given any input, you can predict the output by just tracing the information from in the forward direction. It's called the forward direction because that's the direction of all the arrows. Now, given, let's say that we have an example x that has the true label y star. So I don't know if you can see this, but the true label is the number y star. It's a number because we have a regression problem. Remember, the output neuron is a linear, so it's a real number. So we can, what's a reasonable loss for regression? Yeah?
The difference between the predicted number and the actual number.
Well, the difference can go, the sign matters. You can take the absolute value of that. Absolute value is slightly a problem because it's not differentiable. So most commonly, what do you use? The square of that. So you can write down the square loss for this particular example as the square difference between the prediction and the ground truth, half because we're going to take a derivative. So given a particular example, if you had all the weights, you can calculate the value of the squared loss. Now, the goal of learning is to minimize the total square loss over the entire training set. Remember, this y is dependent on the choice of the w's. All the w's. If I change the w's, the value of y changes. It's the same y as that. So this L here is dependent on all the w's. So L is really a function of the w's, right? So L is a function of the w's, and I can now train a classifier using whatever methods we have. How do we optimize such a function? Or have we optimized such functions in the past? For, say, logistic regression or SVM. Not you, because you've spoken a lot. Someone who's never spoken this semester, because we only have one more week. Then after that, if you want to talk to me, you have to find me. How do we optimize these functions? For someone who has spoken infrequently this semester, just to kind of lower the bar. Yeah?
We could do stochastic gradient descent.
That's exactly right. We could do stochastic gradient descent, and in fact, that's what we will do. I do want to point out that what I will present now is the simplest stochastic gradient descent version. There is a whole family of variants of stochastic gradient descent that I will just mention by name. And in fact, if you're using neural networks, you will probably be using one of those things. But the underlying ideas are still the same. The underlying idea requires us to essentially initialize the parameters in some way, and then you do multiple passes over the training data. In each pass, you shuffle the training set, you iterate over all the examples. Maybe you iterate not over the examples, not one at a time, but in what are called batches. But in the simplest version, you just iterate over one example at a time. You treat this example as the entire data set. You compute the loss you compute the gradient of the loss for that one example, and you update the weights. The way you update the weights is you take a step in the negative direction of this stochastic gradient. So you've seen this before. This is the same template that we've been beating to death all the semester. And this is the same caveats that we had before apply. This learning rate gamma t is it's a choice that you make. There are many possible tweaks. You are trying some of those in your homework. In practice, you'll hear other names. You'll hear names of algorithms like Adagrad, which help choose the best learning rate in a slightly more clever way than just picking something and hoping it works. But picking something and hoping it works is also as good as anything else if you have convex functions, and that's where things break down. For SVM, the objective that we were optimizing was convex. For logistic regression, you can convince yourself offline the objective that you are optimizing in your homework is convex. Same thing for perceptron, and a lot of in general, any reasonable objective function that we have for linear models is convex. Not true for neural networks. Anything that is for most non-trivial neural networks, the objective is not convex. If you want a picture for what that might look like, a convex function is something that might look like this, where there's only one minimum, and you know that you're going to get to it. You just go down the gradient. Non-convex function might be something like this. If you start here, you could end up here. If you start here, you will end up here. Right? And some people like to visualize this as you have a bunch of hills and you have a ball rolling down the hill, and the valley that you get to depends on where you start. So what that means really is for neural networks, the initialization of your parameters can be extremely important. So what people do often is they don't just initialize it once and hope it works, or they don't just initialize it to 0. They initialize it to random points, and there is a whole set of folklore, let's call it, on how best to initialize neural networks. Today, apparently, the best thing to do is what is called the Xavier initialization. If you're using any self-respecting neural network library, they'll just let you do this automatically. But it just gives you one initialization, and maybe the initialization was wrong. It's essentially a random initialization. So what you do is you do this multiple times. You randomly initialize multiple times, and you run all these gradient descents to the bottom to their best values, and you compare the objectives. Is this better, or is this better, or is this better? This looks like it's better, so you go to that. Or you use another way of finding the best one, which is you could, for example, use the one that the initialization that leads to the classifier with the best validation set performance. Or you could use an initialization. You could use all the initializations you get. In this case, let's say you get 3 different classifiers. You can ensemble them. You can have them all vote on the answer. So which of these is the best? It depends on how much compute you have. Personally, I prefer ensembling them because that tends to work better. But again, it's a matter of taste. So we've solved all the problems. Now all we need is to implement this stuff. What's missing? Have we solved everything? Nothing's missing. Yeah.
Computing that gradient seems non-trivial.
Computing that gradient is non-trivial. Now, this is actually kind of fun because if you think about it, what I'm asking for is the gradient of a neural network with respect to the weights. Or actually, it's not the gradient of the neural network, it's the gradient of the loss associated with the neural network. And maybe today I want to try a 2-layer neural network, and tomorrow I want to try a 3-layer network, and day after tomorrow I just go crazy and I want 150 layers. And in each instance, if you're going to be computing the gradients by hand like we did for SVM, well, you're not going to be happy. So, if the neural network is a differentiable function, or maybe a sub-differentiable function, at least our understanding of what differentiability means tells us that there is a gradient. We know that differentiable functions have a gradient. This gradient is decided by, but the shape of the function is completely decided by the architecture, the nature of the graph, and the activation functions you use, and the loss function you use. SVM and logistic regression can be seen as a one-layer neural network. A logistic regression is a one-layer neural network with sigmoid activation. In that case, you can compute the gradient, and you are computing the gradient of logistic regression, the log loss, in your homework. So one-layer networks are easy. When I said 150 layers, I was not even joking. A recent paper for image classification did use 150 layers. And I can assure you that the grad students were not computing gradients all the time. So what we need is a systematic way of computing gradients. What we need to think about is, can we now, the process of computing gradients seems like it's a mechanical process. It seems like it's just some algorithm that can be applied. What we need is an efficient algorithm for computing gradients, and that's the backpropagation. Backpropagation, you may hear about it a lot, but it's nothing more than a method for computing gradients of neural networks, or actually loss functions. Now, it's calling it backpropagation makes it sound cool. A much less cool name for it is reverse mode automatic derivatives, and that's what it is. It used to be called that in a different community, and then the neural network people reinvented it and called it backpropagation. The literature, if you want to look it up, look up automatic differentiation. Wikipedia has a very nice article on it. It turns out it was actually the first instance that I found was of the same algorithm but not called that, was a PhD thesis from 1970 from Helsinki. And to my utter shame that I can't even remember the name of the person, because backpropagation is so much more popular. So let's just do a checkpoint of where we are, because the next thing that we see is going to be rather involved. If we have a neural network, namely, when I say we have a neural network, I mean we have all the weights also. We have the architecture, we have the activations, we have the weights. Then we can make a prediction for any input. This is called the forward pass. This is just, go from the bottom to the top and you get the label at the top. If you have the true label for an example, then we can define the loss for that example. The loss is a function of only the weights. The loss is a function of the weights for that example. The loss for that example, you can get that. It's a function. And if we are not particularly, if we are kind of not particularly hard on ourselves, we define a loss function and a neural network that is completely differentiable. Today, the terminology that's used is end-to-end differentiability. It's a function that is differentiable all the way from the top to the bottom. That just means it's a differentiable function. But if it is a differentiable function, we can take the derivative of the loss. If we could take the derivative of the loss, we could plug that gradient into stochastic gradient descent or one of its generalizations, and we can learn. So if we have a neural network, we can make a prediction. If we can make a prediction, we can write down the definition of the loss. If we can write down the definition of the loss, and we can take its derivatives, we can take the gradient. So the only thing that's needed, that's stopping us from, implementing our own neural network library, supposedly, is our inability to take gradients. So let's fix that. Are there any questions before we get into the backpropagation of it? Not, we're going to spend most of today's lecture talking about most of what's left, talking about backpropagation. So, at the heart of it, backpropagation is repeated application of the chain rule for derivatives. All of you have seen the chain rule, I hope. You've seen the chain rule, right? So, you might see pictures like this. I really like this version of the pictures that Richard Socher made for a tutorial that he had, so I'm going to use that. So suppose z is a function of y, and I'll use an example to illustrate this. Suppose z is a function of y, and y itself is a function of x. I can write this down as this, what is called a computation graph. X goes into y, and y is computed. Y goes into z, and z is computed, and so z is a function of x. And let's say our goal is to compute the derivative, the partial derivative of z with respect to x. As a concrete example, let's say y is, let's say, x squared, and z is, let's say, log x. No, not log x, but log y. Let's say z is log y and y is x squared. Both of these are differentiable functions. I can calculate the derivative of y with respect to x. It is just 2x. And I can calculate the derivative of z with respect to y, which is 1 over y. What we want is the derivative of z. I'm using b, but in practice it's also always going to be the partial. Derivative of z with respect to derivative of x, you can write it as derivative of z with respect to y times derivative of y with respect to x. Which means it is, we've already done both of these things, so it is 1 over y times 2x. And you can verify that this is correct, because y is really x squared. So far so good. This should not be magic, right? This should be painfully obvious, I hope. Okay, let's make this slightly more complex. Now, let's say z is a function, is actually z is a function, is the sum of two things. It's the sum of two things. It's the sum of one function of y1 and another function of y2, where y1 and y2 are themselves functions of x. So it might be something like z is, say, y1 squared plus y2 or 4. Oh, you know what? Let's put a log in there. It's because we can. Still not a complicated thing. It's just a small function. And y1 and y2 are functions of x. So y1, let's say, is a function of x. Let's say it is e power x. And y2, let's say, is tell me a function that is simple for derivatives. Sin x. Now, the derivative, what we want is to compute the derivative of z with respect to x, but it does not directly, now things might be a little bit more painful. But each of these things you can easily compute the derivative of. The derivative of, now I realize, now I don't have space. I should have written smaller or used even easier functions. But let's just see what we can do. The derivative of z with respect to y1, I'm just going to write them by the side of this graph, is this is 1 divided by y1 squared plus y2 power 4 times 2y1. And this one is 4y2 cubed 1 squared plus 4. Here it's just e power x is the derivative, and this is minus cosine x. Right? I can calculate each of these derivatives easily. And now the derivative of z with respect to x, what you do is you go back along each of these paths. Multiply the derivatives. So you multiply all the derivatives you encounter along the way. You multiply this thing, this, multiply this thing with this, and you add them up. And what you get is the partial derivative of z with respect to x. This seems like a very mechanical process. This is correct. I mean, this is not just correct. It's not terribly hard to prove that this is correct. But the good thing is this is mechanical, which means we can actually write some code that does this. What you do is, in order to compute the derivative of z with respect to x, you first compute the value of y1. You compute the value of y2. Now you compute the value of z. Once you do that, you start going backward along the same paths that you came in. So you take all the paths from z to its parent. So the path from z to its parent you come calculate the value of the derivative. So you store this value on this node, you store this value on this node, and then you go back to its parent, you keep going back to the parent till you come back to the node that you started off with, and you keep multiplying the derivatives as you come along. And anytime you come to a node that has two things like that, two branches going out like that x there, you add them up. You add up all the products that came along the way. This is a rather boring step, but it's good that it's boring because you can actually, you can see how a program might do this. But who said that 2 is a special number? You can do this for when you have many such branches. If z, I'm not going to do this with an example because I'll lose my mind. If z is some function, let's say some fi of yi, where each yi is say g I of x, then I can calculate the derivative of z with respect to x. It's simply the sum over I d I times the, in this case it's g, right? I, because y is really g. And this is again the chain rule. This is just the chain rule that you've all seen, maybe, I don't know, in 3rd grade. No, not anymore. But it's the same thing that you encounter all the time, but this is the mechanical version of this. So what you do is, again, you run the forward paths, you calculate all the y's and the z's, and then you trace all paths back to where you want to get to, and you keep track of all the partial derivatives, and you keep multiplying them when you encounter a new edge. Any questions before we put all this together into backpropagation? Yeah?
Can you just keep the current derivative and forget about all the past ones?
Sorry, say that again?
So say you're at, I don't know, d of y.
Let's use the smaller example if you want. Yeah.
Say you're on the hidden layer.
Uh-huh.
Can you just compute the derivative at that point?
And then? So x and y and z's are not hidden layers. This is not supposed to represent a neural network. This is just supposed to represent any arbitrary computation, any differentiable computation. It turns out we will need to compute the derivatives not with respect to the nodes, but the edge weights in what we have, because the edge weights are associated with edges. So you can't stop somewhere in the middle because you need to go all the way to the bottom of the network, because there are some weights that are trainable there also. So you have to essentially span the entire network. Yes.
You said mostly the activations these days are radius. How do you compute the derivative?
Oh, you use the subderivative. The subgradient of the ReLU is the threshold. Let me not ruin the slide anymore. I just saw this. I just saw what you see. It's hideous. So let's go to a different slide. Let's zoom in. So the ReLU is max of 0, x. What is the subgradient of this? You want the derivative of this with respect to x. It's either 0 or 1. When this is when x is less than 0, this is when x. So you use the subgradient. This is the same idea that we use for the hinge, for example. Other questions? If not, I'm going to just instantiate the same thing in the context of the network that we saw. So if you had any questions in this sort of an abstract thing, hopefully they'll disappear once we ground it to the concrete network that we have. So what I'm going to do now is implement show you how backpropagation works on this network that we had, in order to calculate the gradient of the loss. What we care about, keep in mind, is that we want to update all the W's. We need to update all the W's, which means we need to compute all the gradients with respect to all the partial derivatives with respect to the loss, of the loss with respect to each of the weights. So we need the partial derivatives of L with respect to all the output layer weights and all the hidden layer weights. And in a more general network, we will have like millions of such parameters in real life. So we need to calculate the derivative of the loss with respect to all the parameters that exist in our network, and let's do this one at a time. So the way to think about it is you don't proceed, randomly. You don't say, okay, now I want to compute the derivative with respect to this, then with respect to this, then go here, maybe then go here. No, you just go from the top to the bottom. In the forward pass, we went from the bottom to the top. In the backward pass, we go from the top to the bottom. So let's start off with this process. And at each step, what we will do is we will keep applying the chain rule. We'll keep applying the chain rule to compute the derivatives. And any derivative that we compute, we will not use it and throw it away. We will remember it. We will remember it so that in case we need that value again, we don't have to recompute it. So this is memoization. So let's see how this works. Let's say I want to, in all cases, remember, I want to compute the derivative of the loss function with respect to the weight. So I'm writing down the loss function and the weight at the top. So we want to compute, let's say, the derivative of L with respect to this weight here, WO01. Now L, it seems, if you look at it, is not really a function of WO01. It's just a function of the Y. Y happens to be a function of W, the thing that we care about. This is the same situation that we had before. We have L is a function of something, and that something is a function of what we care about. So we can apply the chain rule. So the partial derivative of L with respect to that weight is really the partial derivative of L with respect to Y multiplied with the partial derivative of Y with respect to that thing that we care about. Now each of these things is easy. So the partial derivative of L with respect to Y is just Y minus Y star. Y star is a number, keep that in mind. Y star is the ground truth, is the true label that we are given. So the derivative of L with respect to Y is just the difference. And then now we need to calculate the derivative of Y with respect to WO01. Thankfully, that's just 1 because it's just a linear thing. And now we know the derivative of L with respect to WO01. It's just the product of these two things. So the partial derivative of L with respect to WO01 is, right? Because it's just a product times 1. It's just a product of that. So we're done. We've done with calculating that derivative. Yes.
So the loss function is multiplied by 1 half instead of just the square. Is that just to make the derivative simpler?
That's exactly it. So that it's to avoid programming bugs where we might forget to multiply by a half. That's how I rationalize it. It's to avoid actually errors in the process of taking these derivatives if you were doing it on paper, because you might forget to carry the half around. Yeah. And it's a constant, right? I mean, you can multiply by any positive number. The W that maximizes it or minimizes it is not going to change. It's as long as that number is positive. Yeah. And that's usually the case whenever we have squared loss. So we saw this probably with the, we saw this with the regularizer, W transpose W. There was a half that multiplied with it because, W transpose W is basically the square of W, or the norm of W squared. So the half will get cancelled out. So what we have here is one of the many, many partial derivatives that we need to compute. But at this point, technically speaking, we can make a gradient update for W01, because the gradient update for W01 is minus some learning rate times the gradient. But most of the time, we will not do this right away. We compute all the gradients and then do the updates. But I just wanted to remind you that this is why we are doing it. Let's do one more example. Let's do the W11 for the thing that's highlighted in blue there. Again, the same story. L is not a function of W11, but L is a function of Y, and Y is a function of W11. So the chain rule applies. And so you calculate the same derivatives again, derivative of L with respect to Y is y minus y star. Derivative of y with respect to W011, in this case, is not 1, but it's Z1 because it shows up here. Now, we know the value of Z1 because we've already done the forward pass. We've done the forward pass, so we know the values of all these nodes. So, in order to apply backpropagation, first you need to do the forward pass so that all the Z's and the X's and all the hidden and the outputs are available. At that point, you can actually just read off this number. Now, there is some amount of optimization that you can do. Well, the gradient here is to complete this is the product of y minus y star times Z1. But at this point, you should notice that this process of computing y minus the computation that's expended to calculate this value of y minus y1 is, you don't need to repeat it because we already did it when we computed the gradient of W011. So we've already computed that partial derivative. So why do that work again? Why not save it? So you can save that partial derivative. Maybe if you're thinking of what kind of a data structure to use, you can save that partial derivative inside that node. So that the next time you encounter it, you just use the saved value. This is the idea of memoization. Memoization is the greatest trick in computer science, and it shows up here all the time. So any partial derivative that you've computed, you save it so that you save some work. Now, you might think, it's just one difference. Why bother? It's just y minus y star. Instead of saving it, I could recompute it. But imagine that you have a 150 layer network and you're somewhere deep in the network. You don't want to recompute the whole thing again. So you saved it and you have that value. And so you can calculate this thing with fewer operations. You can do the same thing, you can do this for this W whatever. Now, let me just run through another example. This weight in the hidden node. At this point, we have to do a little bit more work because what we want is to calculate the derivative of L with respect to W22H. I'll just call it the weight. W22H is a lot of stuff to save repeatedly. So I want to calculate the derivative of L with respect to that weight, but L is not a function of that weight. L is a function of Y. Y is a function of all these other things. In particular, it's a function of Z2, and Z2 is a function of, what did I miss? Z2 is a function of that weight. So I need to calculate the partial derivative of L with respect to Y with respect to Z2, and Z2 with respect to W22, and that way I'll get the same. So I want to calculate this partial derivative, but it's really the derivative of L. At the level of L, I have no notion of W22H. L is just a function of Y. So I can only take the derivative of L with respect to Y. So that's what I take, and then hope that Y somehow connects to the weight that I care about. Turns out Y connects to the weight because Y is just this quantity here. So I can calculate that partial derivative. And just to simplify things, I'm going to just compute the derivative here. It's with respect to W22. If this thing disappears, it's a constant. Maybe W22 is a function of Z1, or maybe W22 is a function of Z2. Yes?
So the stochastic gradient descent, the y is going to change at every update, right?
Oh, yes.
So when you're saying to cache a weight vector, you're saying just as you move down that specific.
Not the weights, you mean the prediction.
For the next update.
That's exactly right. All the caching happens for this particular example. Once you see a new example, you erase all your caches and you start from the beginning. That's perfect. Yeah. So we have this, and now I can calculate the derivative of the partial derivative of Z1 with respect to the thing I care about, and the partial derivative of Z2 with respect to the thing I care about. Z1, thankfully, is not a function of the thing I care about, so that partial derivative disappears. So I'm left with just this quantity here. So I have the partial derivative of Y times W21 times the partial derivative of Z2 with respect to the thing I care about. Z2, remember, is a sigmoid activation function. So Z2 is really sigmoid applied to the dot product. I'm not going to write the dot product because that will involve a lot more writing. So, oh, and also because I wrote it. Z2 is this thing here. I can now calculate the derivative of Z2 with respect to W22. You can do it in one shot, but because we have this mechanical way of computing dot products, let's see how that goes. Z2 is a function of this thing called sigmoid. Sigmoid depends on W22. It's a composition of two functions. It's a composition of the sigmoid applied to the dot product. So let's say that the dot product is called S. So Z2, I can write it as Z2 is sigmoid of S, and S is the dot product. That thing there. So now I can apply the same game. I can calculate the derivative of Z2 with respect to S and derivative of S with respect to the thing I care about. So I can do this again. This becomes this thing here. It's basically the same process again and again and again. Now, all of you should know how to calculate the derivative of sigmoid because you're doing that for your homework. So the derivative of sigmoid is what? Anyone? It's sigmoid of S times 1 minus sigmoid of S. You should convince yourself that's correct. Now, what I'm removing all the other stuff and just showing you the final thing. The partial derivative of L with respect to the weight is the product of, so there is on top of this there's an L. It's the product of L with respect to Y, that's this thing here, times this weight, that's this here, times the derivative of Z2 with respect to S, times the derivative of S with respect to the weight that I care about. So what we have is, I want the derivative of L with respect to a certain edge. And what I do is basically I keep tracing the path back till I get to the edge. And I multiply all the partial derivatives. That's what I've done here. I've multiplied all the partial derivatives. The good news is each one of these partial derivatives is trivial. We already know how to calculate the partial derivative of y, of L with respect to y. The derivative of sigmoid, I just told you what that is. And this quantity, this thing here is just a linear thing, so it's just only x2 shows up. So only x2 survives. So the final answer is the product of this and this, this, and W201. But there's an important point to note. Before the point, like any questions about this? About the partial derivatives of this thing? What I did was the same operation, but slightly more involved because this is just a longer path. If you have a 150 layer neural network, this path will have 150 things. And at that point, it's just impossible to do it on a slide. Any questions? I saw half a hand raise up and then go down. Any half questions? An important thing to keep in mind is I don't need to recompute this value because I've already done that. I did that when I calculated the derivative of the first derivative I needed. I most likely don't need to recompute this value either because maybe I've already calculated this one and Z2 is shared. So what happens is we've already computed many of these partial derivatives because we're going from the top to the bottom. And if we are clever about it, we would not redo the work. We would just store what we already did, and this gives us massive computational gains. So backpropagation is an efficient algorithm for computing derivatives because you remember partial work. Just to very quickly summarize what we saw, well, the same idea applies for multiple layers, but I'm not going to show you the algorithm. I want you to get a feel for it rather than just see the algorithm. It's essentially a repeated application of the chain rule for partial derivatives. All of you are familiar with the chain rule. This is just a mechanized version of it. To do that, what you do is you first compute the forward pass so that you get all the values of all the nodes, and then you compute the loss, and then you take you compute the derivatives from the top to the bottom one at a time. And as you go, any computation that you make, you cache it. Any partial derivatives that you computed, you cache it because you know that they're going to be used in the low layers. And this is an efficient way of computing the partial derivative of the entire computation graph with respect to the weights. Questions? Yes?
From an implementation point of view, you need some sort of math library that knows how to calculate partial derivatives?
No, what you need is an abstraction of that node that remembers. So I could invent a new function tomorrow that is not in your library. So what you need is a node that knows how to compute the value of the function and knows how to store its derivative. And your whole graph is built using those nodes. This is roughly a much more fancy version of this idea as what is implemented inside TensorFlow and such things. Of course, what the math library that you need is really one that does matrix vector multiplications, because to implement these products more efficiently, you won't be doing real number multiplication because you won't be doing one weight at a time. You'll be doing entire layers at a time. At that point, these products become matrix vector products. And so you do need that library. And more generally, you need a library that can do tensor products. That's why the name TensorFlow. These are tensors flowing through the network. Other questions? What we have here is a pretty cool thing because we can now mechanize learning. Backpropagation is a way that lets you calculate gradients. What you need, so remember, I mentioned this a few times. If I can write down a loss function for a classifier, for any classifier, I can define a learning algorithm by using some sort of gradient-based method. Stochastic gradient descent is the simplest version. The only problem that's left there is to calculate the gradients. Now backpropagation solves that problem. But if you can write down a loss function, backpropagation will invent your learning algorithm for you by putting it into the stochastic gradient descent framework. Backpropagation is a recursive algorithm, essentially, if you think about it, that goes from top to bottom by keeping track of these partial derivatives. And most modern libraries implement backpropagation, most modern neural network libraries. I would argue that today's success of neural networks is because of these efficient implementations of backpropagation, because people who are designing neural networks don't have to think about, oh, if I now add a new layer, I have to redo all these calculations by hand. Because backpropagation is essentially doing this process of computing gradients on the fly, you can innovate in the space of the network architectures, which at this point I would argue has gone a little too far, but that's what's happening. It makes it easy, and for example, I was visiting some high school science fair projects last year, and I saw that 10th grade kids have implemented their own neural networks. They don't implement their networks, they just use TensorFlow. And they are innovating in the space of network architectures, which is really cool if you think about it. They don't know how backpropagation works. Maybe they don't need to. I don't know how the C compiler works, and I truly don't want to. I still can use it. So what we have now is the only problem that was left inside this was I didn't know how to compute gradients, and backpropagation has solved that problem. Solved that problem for us. Any questions?
So do you have to compute the derivatives by hand once, though, for every node in your neural network?
That's right. You need to compute the derivatives by hand for every node in the computation graph, let's call it. But the cool thing is every node is simple. You have simple functions that are composing with each other to construct this massive network. Every single node is simple enough, or you can break it down to be simple enough that uses elementary operators. And so most neural network libraries already do that for you. Yeah?
All these nodes are using common functions, right?
Yes.
So the library can just store what the derivative is.
Yes, that's exactly it. It stores all the derivatives. And sometimes, very rarely, sometimes you come up with a new function that's not in the library. But typically, these are small functions that you can very quickly calculate the gradients for on paper. All right, I'm going to stop now. My watch says it is 10:24. That doesn't even make sense. So next week, I'm going to start the next Tuesday's lecture talking about practical things about neural networks, and then spend most of the class introducing what will be your last classifier, namely the nearest neighbors classifier. The reason I bring it to the end is because it's the simplest thing that you'll see, so might as well put it at the end.